like smart recursion. Okay? That's much more difficult, much easier. And I'll explain what I mean by that. In divide and conquer, what I said was you think top down. You think recursively, right? Divide, assume recursion will take care, and then worry about combining. And you implement it that way. Right? I mean, yes, there may be tail recursion and maybe your compiler can optimize. For the most part, you implement that way. Dynamic programming takes a little twist, where it says, it does many things, but one of the things it says is, think recursively, but don't implement recursively. So let me explain. So let me explain a very simple example you may have all seen. So the simplest example of the value of thinking recursively, but not implementing recursively, is the problem of computing Fibonacci numbers. So we know that a Fibonacci number, n, is defined as the sum of the previous two Fibonacci numbers. Right? So usually you start off at 0 and 1. You need 2 starting points because there are 2 things. Right? So you go 0, 1, 1, 2, 3, 5, 8. I don't know if you know this hack for people who come from countries that use metric systems. If you ever want to convert from between kilometers and miles, this is always the miles and this is always the kilometers. The reason why it's kind of cool, it's a hack, it's a heuristic, but it's a very well designed. You're frowning. Think about why. It works pretty well. 3 miles, 5 kilometers, 5 miles, 8 kilometers. You know, I do this all the time when I have to convert kilometers to miles or miles to right? Yeah. I can prove that. I can prove why this heuristic works, but I won't do it just yet. I'll let you puzzle it. Okay. So you want to compute Fibonacci numbers, and this is a beautiful recursive expression. It tells you everything you want to know. If you want to write a one-line recursive algorithm, you would say, you know, compute f of n. If n is equal to 0, return 0. If n is equal to 1, return 1. Else, return f of n minus 1 plus f of n minus 2. And you turn this into your coding evaluator, and it takes forever, and you wonder why. What is the running time of this procedure? It's a recursive procedure, right? So we can write this down. T of n, the time taken to n, is some constant, a constant amount of work, right? But the important stuff is 2 recursive calls. T of n minus 1 plus T of n minus 2, okay? Plus some constant. Now there is a section in the notes on recursion, that tells you exactly how to analyze recurrences like this. It's really, really beautiful. This idea of what they call annihilators. It's like a discrete version of a differential equation. Let's not even worry about that. Let's say, okay, I don't know how to analyze this. But let's say I'm pessimistic or I'm optimistic. If I'm optimistic, okay, look, no matter what, it's going to be less than 2 times T of n minus 1. Because this is the increasing function. Clearly, T of n minus 2 is less than T of n minus 1. So this can't be any worse than that. So this is fine, I'll use this. Okay, what does this recurrence lead to? If I say T of n is less than equal to T of 2 n minus T of 2 times T of n minus 1, all I will end up saying is that this is something like, I'm going to put quotes here because I'm just trying to get a vibe for what this feels like. It's going to look like 2 right? 2 times T of n minus 1, 2 times T of n minus 2, unroll it, right? This becomes 2 times T of n minus 2, which is equal to 2 times 2 times 2 times T of n minus 3. This goes up by 1, this multiplies by 2, this becomes 2. Well, that's not great. Well, let's be, you know, pessimistic. It's okay. I know that it's greater than or equal to 2 times T of n minus 2 by the same argument. Right? But this is not much better either. This is like 2 to the n of 2. So whichever way you think about this, this is sandwiched between one exponential and another exponential. So that sucks. I wrote this 3-line piece of code and it takes exponential time. But I can just reel off the Fibonacci numbers really easily. So what went wrong? Again, this might be obvious to you what you should do. But again, my goal here is not to tell you what you should do, but to understand the process by which you get there. And the way to think about what's going wrong here, well, I don't know. First of all, let me try to argue to you as to why there's something wrong about this. How many Fibonacci numbers are there between Fibonacci number? How many types of calls am I going to make to Fibonacci numbers between 1 and n? There are n different things I might have to call. Right? Why on earth am I taking 2 to the n time to figure this out? There are only n things out there. It makes no sense that I should take exponential time to poke at a set of n things. Because it's a very simple function. It just doesn't seem right. Maybe I need to, I don't know, but it just somehow something seems wrong. So let's try to unroll this record. Right? So I'm calling f of n minus 1, f of n minus 2. So let's see, let's make a tree here. So this means I'm calling f of n. This is going to call n minus 1 and n minus 2. This is going to call n minus 2 and n minus 3. This is going to call n minus 3 and n minus 4. This is going to call n minus 3 and n minus 4. And what you very quickly start to see is that I'm doing the same work over and over. The reason my procedure is taking exponential time is because after I've computed fn minus 2 in one recursive call, I've got to compute in a different recursive call. After I've computed in one recursive call here, I've got to compute another recursive call. So even though there are only n different values I'm looking at, I'm computing them over and over and over and over again, which is totally dumb. Okay? The one thing we do know in computer science is don't redo your work. Right? Do it once and then write once, read forever. Paraphrase the Java thing. So there's something wrong in our design process. But recursion is good. I keep saying recursion is awesome. Recursion is great. Recursion is our friend. What's wrong here? What's wrong here is that we haven't recognized the recursive calls are overlapping with each other. In divide and conquer, we divided. Every time we did recursive calls, there by definition was no overlap because we separated things out. Right? The recursive call on one side never looked at the recursive call on the other side. But here, it's like they're all kind of intermingled. And if somehow I could just store that value the first time I got it, I wouldn't need to do this all over again. So maybe what I should do is I should keep this auxiliary array here, which sort of will store these intermediate values. And I would say something like, my new piece of code would instead look something like, if, let's say we initialize all of them to minus 1, all the values initially. So, and then we write f of n. Right, we say if m of n is, let's see, so again, if n is equal to 0, but you don't have to do that. If n equal to 0, return 0. If n equal to 1, return 1. If m of n minus 1 is not equal to minus 1, then, and store that somewhere. I'm writing very bad code here. I would fail to move it to I don't know if n minus 2 is not equal to minus 1, then store that value. I should probably put an and here. And return a plus b. And if not, return a plus the recursive call for 1. Now this one is going to be a little bit trickier to analyze because we don't quite know under what conditions we have to do the recursive call versus not. Right? The first time we have to do it, after we don't. But if you start looking at this very carefully, what it's saying is that all I need are values that were smaller than n. Okay? So if I unroll this recursion down all the way to the bottom, what it's saying is fill up the values with n. So f of n basically looks like now for I is equal to 1 to or 2 to n. So initialize m0 equal to 0, m1 equal to 1. For I equal to 2 to n, mi is equal to mi plus mi minus 1. You're done, and return mi. That's it. No more recursion. So we designed it recursively. We observed that many subroutines were being reused. We decided to store this subroutine, these pieces that are being reused, and then realize we could completely unroll the recursion and write it backwards till we have a non-recursive procedure. And this idea of thinking recursively but implementing iteratively is at the core of this thing which people call dynamic programming or smart recursion, where you observe that you can reuse work you've done before. So this is also called memoization. This very simple form of dynamic programming. There are more complicated versions you can see in it. But this very simple form is called memoization because you just essentially write these little memo back. Or memorization, if you want to call it that. You memorize answers. Okay? So the Fibonacci example is a simple example, just like sorting. It's a very simple thing. You know how to do it, but it shows you the process of thinking for designing the more complicated things. In other words, design recursively, observe some interesting structure in the recursion, and this is where this gets sort of the magic part. Use that to redesign, re-implement the recursion non-recursively. So almost all dynamic programming algorithms will look like they're non-recursive, but they came from a recursive thinking process. So the final implementation will not reflect how you thought about it. Okay? All right. That's it for today. I'll do more time. I see people working. I will see you all on Monday. We'll continue with that. And now, like I said, I will write down these notes and transcribe them so you'll have a PDF version of this. You know, the video stopped working if you have.